Hello everybody, welcome to CS302 Online. Today we're going to keep talking about heaps and wrap that up, and then we're going to start talking about hashing. So for hashing, in the past I did a video in VR, so I'll send you the link to that, but we'll do a normal lecture. So all of these lectures, by the way, I did the same lectures in the spring, so there's more examples there if you're interested in that. I'll try to do different things this time around. Although for the hashing, I have to think of something different. But anyways, so last time, I showed you what heaps were. I gave you a pretty nice example of a max heap. And then we kind of rushed at the end when we were talking about inserting and deleting from heaps. So I want to pick up from there and show you more examples of that. But first, how about we do a quick review of Heapify and that, because you are going to have to implement a heap for the assignment. I think it's 9 or something, the one that has to do with Edge of Tomorrow, the movie, and that's the first of 2 assignments related to that movie. The second one is far more interesting and cool. This one's more of a teaser, I suppose. So yeah. Okay, so the heaps work by ordering things in a hierarchical way. If you're using a max heap, then the root of the tree is the biggest value of the heap. If you're using a min heap, then the root of the tree is the smallest value of the heap. And then the rule is that the children have to be smaller than the parent if it's a max heap, or greater than the parent if it's a min heap. And duplicate keys can be a child. So like if you have a 5 and you insert another 5 into the heap, then it can be a child of a 5. So you could potentially have 5 child 5. Do we see that here? We don't quite see that here, but we do see definitely multiple 2s and 1s in there, in that example there. But we could just as well have a 1 who has a child of another 1 potentially, such as we see in this one here. Get the laser pointer right there. So that's okay. And so that's basically the heap property. And then the algorithms are Heapify and insert and delete from a heap. And so for Heapify, what you do is, unlike an ABL tree where you should be rotating and balancing as you insert. So like if you insert one thing, you balance and you keep making sure everything is balanced. Do rotations as needed. With a heap, it's different. With a heap, you want to basically, quote unquote, create your tree by just throwing everything at once. Because it's from an array, you just kind of insert everything into the array and then build a resulting tree, which will look something like this one here. And then from there, once you have built a tree, it's not in heap order. So it's your job to basically convert it into heap order. That one's actually already in heap order, but like the first one we started with was not in heap order. So like that one looks to be also in heap order. They all look like to be heap order. I guess at some point we must have drawn a tree that was not in heap order. So that one does not look heap order like. Actually, no, that looks heap order. Well, that's technically not heap order, that green one, even though it's level order, but whatever. So essentially, it's just in random order. And what we do with the heap order is we're going to make it into a heap. And the way that works is you start from the bottom up. And you draw these small triangles like we did, the red triangles and the green ones and the pink one and finally the blue one. And the idea is that you're heapifying the subtrees and building up into the entire tree. So you first start out with the leaf nodes. All the leaf nodes, you heapify those along with the parent. Eventually what you're going to end up with is a node that you're trying to heapify that you've already heapified because you took care of that ahead of time. So for example, if you were heapifying, and even though it's already heap, if you're heapifying this part here, you can do that. But you don't want to do this part because you need to make sure that this is okay before you do it. Otherwise, you're going to have to do extra work. And so that's why you make sure this is heapified. So then when you're heapifying this, you can take this, which you know is okay, and then work it here. But as you do that, it is possible that you might find something that needs to go back down, in which case then you have to refix this. But it's still much better than trying to start from the top and work your way down, because then you get to basically move things more than necessary. And so that's Heapify, and we'll do an example again in a minute here. And then the other two algorithms are deleting from a heap. So with a heap, for example, with an ABL tree, you can delete whatever you want. You look for something, you delete it, you move on. With a heap, you can't delete anything. You always have to delete the root, which is the minimum value called the minimum key, or the max key, which is the max value. Again, if it's a min heap, then minimum key. If it's a max heap, then max value. And that's just part of the rules of what a heap is. Now, you can do whatever you want. You can implement some weird delete something somewhere in the middle. I'm not saying that you can't do that. It is definitely doable as long as you fix the heap afterwards by calling Heapify again. However, in the pure and traditional way of using a heap, and for the purposes of what heaps really are meant for, you really should be only deleting this root value, okay? And what is a heap used for? Well, one of the examples that I gave you is a priority queue, because if you number things based on their priority and then you heapify it, so for example, this heap is a max heap. So let's say the higher the number, the higher the priority that a task should get, such as a process running in a computer. So in this case, this is the highest priority, so it's going to run first. After that, whatever is there is going to be the next one. So the one on the bottom here are the lowest priority processes, and they don't need to run. But if you all of a sudden need to insert a new process there, you can insert it with a smaller number, and then it'll run at the end. Or if you want to give it more priority and give it like a VIP value, then you can give it a high value, and it's going to immediately go back into the root. So priority queues is a very good usage of heaps. But there's another one that I want to talk about today, and so we'll talk about that. But anyways, that is when you delete from a heap. What you do is you take, of course, that root node, and what you do is you replace it with the last value in the heap. So here it was erased because we did that actually in the last class. But if you were trying to delete the next number here, what you would do is you would swap the 77 and the 2, and after that swap, what you do is you have to refix that value, because obviously the 2 is not the biggest number now. The biggest number is probably this 42, right? Because it's in this square here. So it has to be, the next biggest number has to be around here. And so you have to kind of bubble that 2 down all the way down to where it has to fit, which will probably be somewhere around here. And so ultimately, when you put the 77 here, which means it's deleted, you can easily handle that from an implementation point of view, which is just an array, by keeping sort of a top or head and some sort of index variable, some integer index that points to the last valid value of a heap, okay? And as long as you do that, just think about like a stack. With a stack, you don't need to delete things from the stack as an array implementation of a stack. You don't need to delete things when you like pop them out of the stack. You just have to move the head or the top of the stack down by 1. And that pretty much guarantees that you're not reading things that are no longer there. And the next time you push into the stack, it's just going to overwrite the value and then increase the top to point to the next available spot. And so it's the same kind of concept here, that as long as you keep that index pointed to the last valid spot in the heap, or the next available spot, which it's available, so you don't read it, then you can handle that this way. So anyways, that's how you delete from the heap. For inserting into the heap, it's kind of like the opposite. You want to insert in the next available spot, so that would be here. And then from there, you got to make sure that you have to reheap that area. You don't have to heapify the whole thing. You just have to reheap the area and sort of bubble it up to where it has to be, which potentially could go all the way to the root, but might not necessarily go all the way to the root. But even if it went all the way to the root, you're only affecting the 1/2 of the tree. This other side should not be affected when you're doing that. So, yeah. So, like I said, we're going to do an example of that in a minute here, okay? But any questions before we start with the example? And I'm going to go ahead and do letters and numbers. I feel like I remember last time complaining with the numbers. So I'm probably going to do letters. Yeah, because I remember now. This was a pain with the numbers. I kept getting confused between the indices and the actual values. So we're going to do letters. I do see somebody has claimed the extra credit. Make sure you send me a message with your name so that I know who to give the points to. I had somebody claim it earlier and they didn't tell me who they were. And I was like, they told me who they were in Discord, and it was not the real name. It was a Discord name. I was like, okay, but who are you on canvas? You know, so yeah. All right. Okay, so we are going to do a min heap. And we are going to do that on a couple of letters. So let's just write a message. Actually, you know, to make it theme to the ongoing situation in the world, let's make the message "Go vote." Let's make it longer though. Go vote now. Yes. Or today. That's even longer. Okay. So there we go. That's a good message that we're gonna put in. So we're gonna do that in the array. So first of all, we want to put this in the array that's considered to be the heap. So hold on. Take my watch off because it's doing weird things to the iPad. Okay. So we're gonna insert it by making an array. So how many letters are in that message that I put there? Can somebody tell me so that I make the right number of lines? Oh, these lines are not coming how I had hoped. But oh well. $11? Okay, so I have to make all the way to index 10 then. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, thank you, by the way. So, well, you better be right, otherwise you made me erase this. Let's see, so G-O-V-O-T-E. T-O-D. Oh, you lied to me. or did I miss a letter? Oh, no, you were right. I just screwed up because I said index 10, but I'm calling you a liar. I'm sorry. All right. Okay. So go vote today. Okay. So that's the heap. And what would that look like in tree version would be like this. Go vote T-O-D-A-Y. Okay? G-O-V-T. I think I spelled it wrong. Go vote today. Okay, there we go. Yeah. We should have put like commas as characters because it's kind of confusing, but okay, whatever. So this looks like a nice height. It's not too big, it's not too small. Remember, the reason why we can do this is because it's a complete tree, right? Which means that all the levels are full except for the last level, and the last level has all the nodes shifted as far left as possible. Okay, so this fits that category. Okay, and we're building a min heap, which means that we're trying to make things alphabetical. So like the root of this node should be A, and there is an A inside of this, so that should be the end goal. And then at the bottom of this is somewhere going to be like a T and a V and a Y. Those are like the last bottom letter. So what we're going to do first is we're going to heapify this, make it a heap, maybe take some things out, maybe insert some letters in, and do that. But actually, once we build it a heap, I want to show you something cool about this. So yeah, okay. So first of all, let me color code the triangles that we want to do as we heapify this, which is of course start with the leaf nodes that don't intercept with anything. And then from there, the next thing has to intercept with stuff, which is this one. So that's okay. You can go ahead and do that one as a second sort of stage. And then this one is a third stage because you need both the green and the red square, right? If they wasn't touching the green square, then it could be done at the same time. But it cannot. So you're gonna have sort of three sort of stages that we have to do. Now, when you're coding this, you don't have to count these stages or anything. You just basically start from the bottom and then work your way up recursively or iteratively. You can do it either way, whatever is easiest for you to do. But yeah, I do recommend that you think about that this is not kept with pointers. This is kept with indices, right? And there's that rule that like you can find out the parent indices. You know, the child indices, we know we can do like, you know, index of the parent times 2 plus 1, and then index times 2 plus 2. So that's how you go from parent to child. In fact, maybe instead of I'll just P for parent. So we know that we can do that, and then you can reverse this formula to find out where the children are. So this is the left child, and this is the right child. So you can reverse this formula to basically work your way up, right? And remember, it's always in pairs, like that. And then this is the two children, and then these are two children, and then these are the two children, and then these are the two children, and then this, of course, is the root. See that? So these are all pretty much matching. In fact, if I use the same color for them as I did here, it might be easier to see that. I do apologize for the curly braces not being very nice, but I struggle with those. So those are the three red ones, and then we got the green one, and then we got a blue one. I think that's a different shade, but whatever. Okay, so yeah, so that's quite convenient when you're actually coding this, whether it's a loop or recursion. So yeah, okay. So let's go ahead and start with the A and the Y. And so we know that the parent of the A and the Y can be found by essentially subtracting one from either of those, or two, one or two, and then dividing it by half. So basically, let's look at A. Okay, so so that's index 9. So 9 minus 1 is 8, and then divided by 2 is going to be 4. So that is indeed the location of the parent of A and Y, as you can see there. That is perfect where it is. So believe in the formulas, okay? Maybe I'll write them here too. So like left child is equal to parent minus 1 divided by 2. This is, of course, just like trivial algebra, or at least I hope it's trivial to you. But if not, then, you know, I guess review algebra. So yeah, okay. So let me just write that nicer. Well, it looks cleaner now. Okay, so in this case, because we're doing a min heap again, we want to make from the A, the T, and the Y, we want to pick the one that is closest to the smallest one, so the closest to the A, which I guess is an A, and make that the root. So that would be, of course, the A. So swap the A with whatever the root currently is, which is a T. So that's what it looks like in the tree. In the actual array, what you're doing is you're taking this one, and then you're taking this one, and you're swapping them. Like that. And that's pretty much it. You have taken care of that one. So moving on to this one. Okay? Any questions or anything like that? I mean, this is hopefully review. Okay, so from there we move on to the next set, which is the OOD. So that would be this one, and then the parent of that, which is this one. Again, you take 7 minus 1, which is 6, divided by 2, which is 3, or you take the 8 minus 2, which is 6, divided by 2, which is 3. That was one way to do it. If you don't know which parent, which if it's the left or the right child, one trick you can do is just subtract 1 from it. So like, let's say you do the 8, you still subtract only 1 from that. You get a 7, right? And then if you divide the 7 by 2, then you're going to get 3.5. So go and take the floor function of that, and you get a 3 out of that. So yeah, you know, it works out that way. And if you did it on the other side, 7 minus 1 will be 6, divided by 2 is 3, which is the floor function that is still 3, right? So you can just take advantage of the floor function, I suppose, if you do minus 1. If you do minus 2, though, then you got to do the opposite. You got to take the ceiling function of that. So yeah, just make sure you don't get that mixed up. Okay. So anyways, we got the O. Oh, already got the colors like getting all weird. So let's not highlight the colors in the array, otherwise we'll be lost. But we got the O, and the D. So in this case, the D is the smallest one of them. So we want to switch this and this. So that is so easy to get confused. So let me make sure I really make that look like a D. So what we did is we switched the right hand side, so this one, with this one. Okay. I hope we're not sending like, we're not making like some weird scary message here as we're building this. That'd be scary. Like, I was trying to see if that doesn't say anything weird, but we don't have anything that could become like offensive here or something. So yes. Okay. So yeah. All right. So that takes care of this as well. So now we move on to the last red one. So we got EVT, which we can identify by just basically taking 5 minus 1 is 4 divided by 2 is 2. So that means that this is the parent. So essentially we're gonna swap that V with the E. So E and V. Okay. So that is pretty much that one. So moving on to the green one now. This is where things will start to get a little interesting. So here we're gonna take the O and the A and we're going to swap them. So that would be this one and this one. So here's the thing though. In this scenario, after you do this swap, which has happened between this one, I should definitely highlight, so I'm going to highlight it. So we swapped that with, oh, I hope I did the right swap in these letters. Let's see, J-E-E, and then, oh, I think I swapped the wrong letters on the index. Oh, hold on, let me undo. No, actually I did not. I thought I did, but I did not. Okay, so A and O. I think what happened was that I actually forgot to swap these. Yeah, that's what happened. So I forgot to swap these in the drawing. There we go. Because the actual array one was okay, but I forgot to swap the drawing itself. Okay? So anyways, now it looks okay. So here's the thing though. So right now, we just swapped, we were looking at these three letters. We were looking at these three, okay? And we just swapped the A and the O. But here's the thing. When you do that swap, you gotta make sure that that doesn't break the subtree. It's possible because like, while we swapped an A and an O, imagine that instead of having an A and an O there, we would have had an A and like a W, okay? If a W was originally here, and then it got pushed down because of the A to here, then that breaks this subtree right here. If it was a W. Right now it doesn't break it because it's an O. But if it would have been a W there, it would have broken it. So when you go back down and you swap something, and now it's not a leaf node that you just swapped with. So whenever you swap it with a leaf node, you're good to go. So in code, you can check to see if it's a leaf node by taking that value and multiplying it times 2 plus 1 and plus 2 and see if that is out of bounds of the array. If that is the case, then it's a leaf node. Or by the way, it doesn't have to just out of bounds of the array. It can just be that it's greater than the number, again, that you're keeping track of as your index, right? As your max value, which in this case is 10. So you keep it there, you keep it pointed at 11, doesn't matter, just make sure you do the right logic, plus minus 1. So as long as you do that, then if it's out of bounds, then you know it's a leaf node, right? You can't check for null because again, this is not pointers. So if you do that and if it's a leaf node, you're good to go. But if it's not a leaf node, you need to recheck that subtree to make sure that it did not break. So in this case, we have to go ahead and take the 4, multiply times 2, get the 8 plus 1, get the 9, and then, multiply times 2 plus 1, 4 times 2 is 8 plus 1 is 9, so it's actually 9 and 10, okay? And then, of course, you compare that and you see that it's okay. If it's not okay, then you make it okay. But in this case, it's okay, so you're good to go. So now you keep doing this and checking each of the two children. You multiply 9 times 2 is 18, plus 1 is 19. That's bigger than my max, and it's out of bounds, so you don't worry about it. And then 10 times 2 is 20. We got to finish looking at t. So we look at 19 and 20, and then we look at 21 and 22 to check both children's. Both of them are leaf nodes, so we're okay. So notice that I had, let me do that again slowly. So to make sure that T and Y are leaf nodes, I gotta take the index of T, which is 9, and multiply it times 2, add 1 to it, which gets us to 19. And that's the left child, but I gotta make sure it doesn't have a right child. It shouldn't, because it's a complete tree, but if you want to be extra safe that no weird things are happening, then you can check it. Which of course there's nothing because it's bigger than 20. Same thing with the Y. You gotta check and make sure it has no left or right child, which it really shouldn't. If T had no left child or right child, then Y is not gonna have any. But again, you could be extra safe and then just check it. Index is 21 and 22. Okay? So anyways, now that you've reached leaf nodes, then you know this is good to go. So you have completed yet another step. Finally, we get to the last part of this, which is the blue one, the G, A, E. In this case, you have the A and the E, which need to be swapped. Sorry, I said A and E. A and G would need to be swapped. So A, G, what that looks like is this. Okay? And when you do that, then you have to again recheck the subtree, which in this case, something is going to actually happen, because as we see here, the G and the D are not in the right spots there. So that's good, because now we can actually show you happening that. So in this case, we look at the G and we look at the D and we swap them. Now, why did I swap it with the D and not the O? Because you want to get the smallest one of the two so that the heap property is maintained. And then you look at the red square, but nothing needs to be swapped there, so you're good to go. So we have completed the Heapify algorithm. So that was Heapify. Okay? Heapify has built a heap. Is this a heap? Well, look at each of the triangles and see if they follow the heap property. A is bigger than D and E. E is bigger than N and T. By bigger, I mean smaller, sorry. A is smaller than D and E. E is smaller than N and T. D is smaller than G and O. G is smaller than O and O. O is smaller than T and Y. So we're good to go. Great. Okay. So before I do anything, let's go ahead and actually remove everything from this heap and see what happens. Okay. So how do you do that? Again, you swap it with the item at the end. So let me just copy and paste this so we have this left behind, because I do want to go back there and maybe insert some things. But let's go ahead and have some output. So this is where I'm going to put my output as I go, and remove each thing at a time. Or in fact, actually, no. I don't even need to put an output. I can, since I have the array, let me copy down this array. I'll leave it in place. Okay, so what I'm going to do is I'm going to take out each thing from there, from the heap, which will, of course, slowly decrease my max, which I'm going to currently point to the last valid item. I've made that as a decision, implementation decision, okay? Make sure it's not like in the middle between two things. All right, so again, when you delete from a heap, you only delete the key that is at the root. It's called a max key or min key. In this case, it's called a min key. Shouldn't A be first index instead of E? Oh yeah, that's a good point. I forgot to do that, I guess, or I don't know. At some point I didn't do that in the swap. Yeah, I don't know. I forgot to do that here. My bad. I think I think what happened was I swapped it with the wrong E inside of here or something. I don't know. Who knows? Is everything else okay? Geo. This is a V, not an N, actually. It's misleading that it looks like an N. And then G-O-T-Y. Or is that a G or no, it's an O. So, okay. All right. Everything else is good. Good catch on that, though. Thanks. Okay. So, all right. Let us go ahead and delete the min key, which in this case is the root. So what we do to delete it again is we swap it with the last item. So the A and the Y are going to get swapped like such. And so we want to decrease the max to point down to the one before it. So in this case, the T. And what that looks like in the drawing is the Y and the A get swapped like such. After we do that, after we delete the main key, we need to fix the heap. Now, we don't call the Heapify function again. That's overkill. We don't do that. We just need to bubble this. This is called bubbling up or bubbling down. In this case, we got to bubble down the number to the right spot. Okay? And this may seem at first to be highly inefficient because you're like, if it's at the bottom and you just swapped it with something at the bottom, this is like one of the biggest numbers in this heap. But now it's over there at the top. This seems very inefficient. It's not. You have to trust me on this. I can't really prove it to you without spending like an hour here or something, but you just kind of have to trust me that this is efficient, okay? This is pretty efficient. And we'll talk about tech complexity in a minute here when we finish this example. But yeah, it's pretty efficient that way, okay? So what's going to happen now is you basically just heap that by bubbling it. So you got YDE, pick the smallest of the two, in this case is the D, and swap it with the Y. So what that's going to look like is Y and D swap. And then now we know for sure that this side is okay, but we need to fix this part and then potentially fix these and these, one of the two only, based on where this goes. So in this case, we pick the smallest one. G is smaller than O, so we pick that. So then Y goes there and G goes there. So Y, G. From there, now we gotta fix this one. And it might not, by the way. If at this point, like, it was okay, then we don't need to keep going. But because something did swap, we need to make sure it's okay. And in this case, we do have to swap. But now here, it's an interesting thing because both letters are the same, right? Like, O is the same on each one. So in this case, it doesn't quite matter where you swap it with. So just pick one of the two. I went with the left side, but it could have just as well gone on the right side. This is not, again, it doesn't matter the order of the children. It can go on either side. There's no predefined thing like with an AVL where like duplicate goes on the left and so on. There's no such thing here. Binary search tree. So you just put it on one side, okay? And you have to make a choice because when you're coding, you have to put a choice, right? Unless you call like a rand or something. So just choose left. Yeah, probably left is better. So, yep, okay. So that pretty much concludes it. It's back to being a heap and we're good to go. So now we're going to head and keep removing. So the next thing we're going to remove is again the root. So we swap the root with the last valid item, which in this case is the T. So D and T. And then decrease this. And then, so I remember that those don't count, I'm going to highlight them with a gray. So those marked as no longer part of the heap. Okay, so we did that. So now we got to bubble it to the right spot. So that is going to be going this way this time because E is smaller than G. So we get ET. And that looks like this, T and E, ET. Now, we don't have to worry about fixing this side because this went this way. So they only have to worry about looking at this. In this case, T is equal to T, so no need to swap there. And then T and V, T is smaller than V, right? Yeah, so in which case, we don't need to swap that at all. So that is good to go. All right, that was easy. Let's go ahead and do another one. So in this case, we're going to take the O and the E. So O and then the E. Now that E was... Why do I have an 8 still there? I forgot to swap that, I think, at some point. Oh, no. It's just that I put that there. Okay, yeah, all right. So, yeah, okay. I panicked for a second. We're okay. Move this one more to this and basically fix it. So now I'm going to start going faster because otherwise it will take like forever to do this. So, yeah, so OG is going to swap. So GO, that will look like this. GO, and then we're good to go. Now we gotta, that's cool. We put all the O's together in the green triangle. So because there's no swap that happened here, you know, once we swap the green one, we check, when we swap the blue circle, we check the green circle. In the green circle, there was no swaps. Because there's no swaps there, we don't need to keep going and checking any of the red circles or triangles. We're good to go at this point. So yeah, it's efficient because there's no more checks needed. Okay? Cool. All right. Now, next letter, G and Y. And then move the max one more this way. So mark this G as done. GG's. All right. So from there, we got to swap the Y with the O because it's smaller. So that is going to look like here. And then this time around, the green does get updated. So again, we just pick one side. So let's just pick here this way to be consistent. So we got the Y there and we put the O there. And then that will look like, in terms of drawings, we will have this one swapped with this one. And there we go. At this point, we don't need to do any more swaps. Now you might be thinking, but wait a second. Like, this doesn't look right. This doesn't look right. Well, remember, this is no longer part of the tree. And we know that because of the max. So really what we're looking at is like this. And yes, in this scenario, this looks right. This looks like an okay heap. So remember, you don't try to heapify, or you don't try to fix the heap property in stuff that's no longer part of the tree. It's still there because remember, when you delete something, you're not really deleting it. You're just marking it as not being used, right? And in this case here, it's even more than that because it's just, you know, you have your integer that keeps track of what is valid and not. So it's still there technically, but you don't, it doesn't exist. You just kind of like block it out from your mind. Okay? So, all right, let's keep going. So now we're going to swap the O with the T. That's the next value in the level order here. So and then move this by 1, and then because of that we mark that as used, and then fix the heap. So O and T swap, and then we swap the T and this O. So swap this one with this one. Hope I'm not making mistakes. I'm going kind of fast here. It's just hard to keep track. I mean, if you were just doing the tree, you'd be good, but doing the array is like, ugh. But I really want to show you that because the array is what you're kind of implementing, and just showing you the tree might like get you lost when you transition to actually trying to code this. So yeah. Okay. So anyways, that takes care of that. So as you see, it starts to get a little better now because we're not, you know, we're looking at just 3 triangles, and pretty soon we're going to be looking at just 2 triangles. So you'll see that we're almost actually done. So we swapped that with that because we removed the next number. So we're going to mark that as done. Move this over, but make sure we swap before we do that. So V and O. Okay, so now we're actually only looking at 2 triangles now, which is cool. So that'd be nice. So let's go ahead and swap the O with the V. And are we good there, or do we need to do one more? The T needs to go to the top, right? Yeah. So T goes to the T for top, I guess, and then V goes on there, right? So that is going to be here swapped with here. Okay. So we still got one more O to do here, so that's going to be the next thing. So swap that again with this V and put the O there and mark it as done. That basically means swap this and this. So VO, move this max. And so now fix the tree, which in this case, nothing needs to be fixed. So that was quite convenient actually. So, right? No, wait. It does need to be fixed. Because, yeah, all right. So T and V need to be swapped. T goes before V in the alphabet. So. Okay. That's it, because then the V and the Y don't need to be swapped. So almost convenient. All right. So next we take out the next thing, which is the T with the Y. So T, Y. So T, Y. Move max. It keeps like sliding down there. It's annoying. And then mark it as done. Okay. So now we're only working with one triangle, which is the blue triangle. That's all that's left in the heap, like those three like that. So that's quite nice. So let's go ahead and just fix that heap. So take the smallest one, which is the T. So that becomes TY. Okay? So let's go ahead and delete the next thing, which is going to swap the T and the Y again. And then move this by 1. And then mark this as done. And then fix the heap, which means move the V and the Y. Okay, and finally we delete one more thing, which is the V, which gets swapped with the Y again. This is normal. I guess I forgot to update those, but sorry, what did we have before? I got confused. It's erased a couple of times. Okay, so that's what we had. So we had this fine. Okay, so we're gonna delete one more thing, which is the V. But to delete it, we have to swap it with the Y, because it always goes with the last spot. So we swap it like that. Y, V, there we go. Move max by 1. Mark the V is done. And then fix the heap, which in this case is just a single item. So when you have a single item in a heap, it's just good to go. All right, finally the last thing is we delete this, which you swap it with itself. Swap with yourself. Y swaps with Y. And then mark Y as done, and then fix the heap, which is empty now. So when the heap is empty, you know you're done. So check this out. Let's look at the numbers that we just printed. We printed YVTTOOOGEDA. What can you tell me about the ordering of those letters in comparison to the original message, which was to go vote today? So what's special about it? It's reversed, but it's not just reversed. It's sorted in descending order, right? Or in non-ascending order. So we have sorted the numbers. And guess what? If instead of doing a min heap, we would have done a max heap, we would have seen the list in a sorted well, I might have said it wrong earlier. Right now it's a non-ascending order. If we've ran this with a max heap instead of a min heap, and we would have seen this array, it would have been sorted in a non-descending order. So in other words, we would have sorted it in ascending order. So we would have seen A, D, E, G, O, right? But either way, right now we want to flip it, we can just flip it with a single pass, right? This is known as Heapsort, and it is another sorting algorithm. So congratulations, you've learned another sorting algorithm. So how good is Heapsort? Heapsort takes n log n time like merge sort does. So it's pretty quick up there with merge and quicksort. It's cool because let's flash back to algorithms. What did we care about when we talked about sorting? We cared about whether it was in place. We cared about whether it was a stable sorting algorithm. And of course, we cared about the big O, the theta, and the omega, right? Heapsort is in place. As you can see, we start out with an array with the string that we wanted. We run Heapsort on it, and it's still in the same array. We just need like a swap variable, like a single car for swapping, right? Now, we did a min heap, so it ended up backwards. If we'd done a max heap instead, it would have actually ended up in order, from like A to Z, right? So essentially, it's an in-place sorting algorithm that does not require anything but a single swap variable. Is it stable or is it not stable? It's not stable because things do move around quite a bit. So I don't think you can make it stable. I just Googled it right now to see if it says anything about stability, but I highly doubt that it's stable. Let me Control F the word stable in this thing and see if it pops up. All right, so it says Heapsort is an in-place algorithm. Yeah, we just talked about that. Its typical implementation is not stable, but can be made stable. So there you go. So it can be made stable, and it has a link. It says see this, and it says stability and sort out. Okay, so yes, it can be made stable. I think. Well, any algorithm can be made stable if we add a second set of keys that keeps track of the ordering, but that's cheating, to be honest. So I don't know. I guess it has to do with the way things get heapified, but no, it just doesn't seem. I just don't see how it could be, but I'll trust them that there's a way. That does not involve adding a second key, which again is frankly cheating. And by that I'm saying, like, okay, if you want to make any algorithm stable, like you want to make quicksort stable, all you got to do is, in addition to having to sorting the letters or whatever you're sorting, add a second key to your sorting algorithm that is numbered based on the order that it came out in. So like, instead of just sorting the letters, I would actually keep track of the original index where these things were at. And so when you finish sorting, you'll see the message like this, but then like these two O's, one of them is going to have the number 7 and the other one's going to have the number 3 in it. So let's say that it was like 7, 3. Then you just do a pass and you flip them because you know that the 3 came before the 7. So if you do something like that, and then there was another O somewhere, 1. So let's say that this one was already at the 1 spot. So in that case, if you end up with the final one and it says 1, 7, 3, then you just swap the 7 and the 3 and bam, it's stable now. So any algorithm, you can do that to fix that issue. So, but I will not consider that stable when you do that because again, you can do it with any of them. I consider it stable when you don't have to do this extra step and still do it. They claim that there's a way to do this. I don't know it. Good luck finding it. If you find it, let us all know on Discord, on Canvas or something. Be nice to know. But yeah, so the other thing is the time complexity of this. So we already talked about theoretically, it's just not possible to achieve faster than, and here, let me give you this link of the Heapsort link. It's not possible to achieve faster than n log n with a comparison-based sorting algorithm. However, n log n is pretty good. So does Heapsort achieve that? The answer is yes. It achieves n log n with big O. And I believe it's all three, actually. Theta and and omega. I believe they are all n log n. Let me briefly check just to make sure, because I don't remember off the top of my head. It just seems like it, but if you go to Heapsort's Wikipedia, it'll tell us. So n log n, where's data? Or where's big O? Oh, I guess technically speaking, if you have a scenario where all keys are equal, so like you're literally like sorting an array where everything is a duplicate, like imagine it's all G's, then it would be n in theory. So, okay. So I stand corrected. I suppose that is a special scenario. So, okay. But more importantly is to analyze as to the why this is n log n. I mean, it's not intuitive, to be honest, because as you saw here, there's a lot of bubbling up and down. Like, you can see that a lot of the times we have this really nice heap, and if we've just taken something else and swapped it with it, we wouldn't have to like bubble the y. Like the y kept going up and down, and the o's kept dancing around, and it was a pain. But it's still better because like we can see the whole tree as one single picture, but the computer can't, and we couldn't if it was like a massive tree with like thousands of letters. So while you might be intuitively inclined to try and swap, instead of with the bottom, to swap it with something near the top because it's closer to the min key, it turns out that it doesn't really work out that way. And even if you don't believe me on that, if we look independently at each of the algorithms, it turns out that heapifying a tree is a very, very cheap operation. It takes log n time to heapify. It doesn't even take n time. It takes log n time. Because you're not looking at each thing individually. You're looking at the triangles. And there's 4 triangles here, essentially. 5 triangles here, okay? And remember, this has to be a complete tree. And if we think about like balanced trees and complete trees, and these trees that are usually almost full, they have the minimum height possible. In fact, heaps have the minimum height possible for a tree. Always they do. Otherwise they wouldn't be a complete tree. And so that is why it takes log n to do versus n time. Okay? So when you're extracting each thing from the heap, so when you're taking out the min key, that is essentially going to take n time for each key. And so I think that's pretty much how you get the n log n part. So technically speaking, yeah. So every time that you extract one thing, it's n. Now, it's not n, it's a little bit less than n, because like the height of the tree is log n, but you're still doing n of these. So you're doing like n log n's, which is how you get n log n. So it's kind of tricky to see that. But if you read in detail like the Geeks for Geeks, or you look at the book, then you can kind of see as to how they achieve that. But I don't know if there's anything else that I can tell you without confusing you. But it kind of makes sense if you look at it. Like, okay, log n to build a tree, and then you extract each one, and then you fix the tree. And that fixing is going to take time, but it's going to take potentially log n time. But you do this n times. So n log n. And then the log n to build the tree is just one extra log n, which doesn't really matter. So it's like n plus 1 log n. In fact, that would probably be the full like recurrence relation or whatnot. If you achieve that, you probably have a little bit of extra because of the heapifying, but then n log n for the actual removal. So Heapsort is amongst the fastest. Merge sort mixed with, I think it was insertion sort, is still faster, or selection sort. I think it's insertion sort. It's still faster, but this is really, really fast. Like quicksort, Heapsort, and merge sort are the better ones. And then of course, Heapsort is using insert sort because once the list is small enough, that's faster. But in the general case, a single use algorithm, if you are not mixing algorithms, then quick will probably be the fastest, followed by merge, followed by Heapsort, I'd say. But those are really close rates, depending on the data, the ordering of the data. If your data is almost sorted, though, Heapsort is not the way to go. It's going to mess things up because you're using. I mean, you might think it's not. Like if you were building a Min Heap, then an almost sorted data would basically do it for you. Like it would build a Min Heap already, pretty much for the most part. But you're putting a max heap, so you have to like flip the data. So it's not very efficient for almost sorted data. Whereas something like merge sort is much better at that. So that probably gives the edge to merge sort. And quicksort is not good at that either, which is probably why Heapsort is using merge and not quick as well. So yeah, okay. So last thing is let's just insert some things into the heap. So let's go back to how they have the heap and do an insert, since we haven't really done that today. So, and then we'll move on to hashing. Okay, so let's go ahead and insert. So anybody want to insert a specific letter here? You have input Z. All right, we can insert a Z. That's easy, but okay. And then maybe like 2 more letters you guys can throw in here. Okay, so we'll do Z while you guys put in something on chat. So when you're inserting at the next available spot, F. All right. So in this case, the next available spot is actually the left of the V. It doesn't quite look like that because of the way I drew this, but there's a left side and a right side to the V. So this is going to be going on the left side, okay? In fact, maybe I can like slightly move this. Just so that it works out better. Okay. Then we have a little bit more space. N. Okay, so we got 3 letters. Perfect. All right, so you inserted the next available spot, which is here. Now, the cool thing about the Z and why it said it's easy is because it's already in the right spot. Because it's a Min Heap, so the Z is like the last letter, so it's going to be a leaf node for sure. Which in this case it is. So like that pretty much handles that. So not very exciting, but it's okay. All right, we insert the F. With the F, now it gets a little more interesting because now with the F, what we're working in is we're working in the subtree right here. So we're comparing the V, the Z, and the F. Before we were just comparing the V and the Z, and of course nothing happened. But now something will happen because the F is smaller than the V. So there will be a swap that happens. I'm not redrawing the array, but just imagine swapping things in the array, okay? So you swap it like that. And then, whereas you were like bubbling down when you were deleting things, you know, you would bubble down from here all the way here. In this case, we're bubbling up now. So because we changed something in this part here, it's a possibility that this part needs to be updated as well. Which, as you can see, actually is not the case here, but it was almost. Because like if F, instead of F, you guys had picked like a C, then it would have gone up to a higher level. Like it would have swapped this with this. But again, in this case, it doesn't swap because F is bigger than E. Now, I know you're looking at the T and you're like, ooh, but that's okay. It doesn't matter. That follows the heap property. It just has to be bigger than E, which F is bigger than E and T is bigger than E. It doesn't matter the relationship between F and T. You don't look at that. You only look at the relation between the root and the child, not the siblings per se. All right, then we go ahead and we insert the N. So that is going to swap because N is indeed upper in the tree, or should be. So we're gonna swap the T and the N. But that's pretty much where it's going to end. So I'm gonna go ahead and insert another A, just so you can see some swap magic going on. So let's say we insert an A. In this case, we are now looking at this tree right here. And so in this case, we will swap the A and the N. And then it'll swap with the E. And that's pretty much the end of that, because duplicates you don't need to swap. You just kind of let them be. But if there was a letter before the A, like, I don't know, A minus or something, then that would go and swap with that. Okay? However, be careful when you bubble it up again, it could mess things up, so you gotta recheck them. So in this case, nothing got messed up. So yeah. Okay. That's it. That's all I got for you on heaps. Does anybody have any last questions? Can you insert after the deletion? You can. What would happen is this. Like, let's say that we delete the end right here. Okay? Or, sorry, delete the end. Let's say that we delete the key. Let's say we're deleting a key. So, you know, the N swaps with the A. And then the A is marked as deleted. And then you fix the N. So to fix the N, you take that with the D, because it's smaller than the E. So you always take the smallest one of them. And then go with the N and the G, because again, you take the smallest one of them. And then from here, you just pick one of them because they're duplicates. So let's just say it ends up there. Okay? This is no longer part of the heap, the A. So like if you were to insert something, this is when it actually would overwrite. So you'd actually overwrite this with, like, let's say you're inserting a W. That's when you would overwrite with that. And you would increase your max in your array. So, and then now it becomes part of the heap again when you overwrite it, okay? So another example, suppose that like all this stuff was like deleted and then you're inserting something. You would insert it at the next available spot, which is right there. So that's where you would insert that, okay? So that's how it works when you delete and insert. So anything else with heaps? Otherwise, we shall talk about hashing. How is this implemented, as an array or as a linked list? As an array, as I've been saying for the last 2 days. That's why I've been drawing all these annoying boxes and having a headache with them, because I want to show you that this is all done through an array. If it was linked list, I would have not bothered with the boxes. So, but yes, you want to do it as an array. You don't want the headache that you get if you do. I mean, this could work as a linked list, but not linked list, but like pointers, which is what I'm sure you mean. But the problem with that is that you'd have to make sure you have pointers to the parent and to the child, and to make sure you can go back and forth easily. This is just so much nicer to implement it this way. Like, there's no reason to do it as with pointers when it's a complete tree, which means you can implement it as an array. You want to take advantage of that. It makes it a lot faster too, because if this was pointer based, going to a child would involve a lot of work, and that would just take slower. It would take longer, not slower. Well, slower, longer, same thing. Okay, so yes. Anything else? All right, let's talk about hashing. So today I'm going to give you an introduction of hashing, and then on Wednesday, it's going to take us a couple of days to do hashing. Probably 2 days. So probably like, well, 3 considering today. So we don't have to deal with pointers in assignment 9. I believe you do not have to deal with any pointers in assignment 9. So yeah, don't worry. You'll have to deal with a bunch of them when you get to the graphs again. So like 10, 11, and 12 or whatever those are. There won't be any, actually, I don't know if there will be pointers with the hashing one. Yeah, I don't know, it depends, because I don't know what we're going to do for the hashing assignment. I still have to figure that out. But yeah, there's no pointers in that assignment. So. But I mean, at this point, you should like transcend your fear of pointers. You've been using them all semester. You should like embrace pointers as your brothers. Sounds weird. Okay, so anyways, hashing. So we got 10 minutes, so it's just gonna kind of give you a taste of the reason of hashing. Okay, so by the way, this is the lecture that I did in VR. So if you're interested in watching that version of this, you can watch that, I suppose, and you know, might get useful out of that. I guess I'll share the link. It's a 26-minute video, but it's part of a lecture. The lecture video is in a different one, but yeah. So the premise with hatching comes with the idea of locating items quickly, right? So why did we spend, by the way, congratulations, we have moved on past trees, so we won't see trees for a while. But let's think about the premise as to why we even talked about trees. Heaps aside, when we talked about binary search trees, the premise behind it was to achieve the best of arrays and the best of linked lists in one data structure, right? Because what are arrays useful for? Arrays are useful for the reason that we use them in the heap, and that is to have fast access time. So arrays have fast access time. The disadvantage of arrays is, of course, a slow insertion and deletion time, right? Unless you're deleting from the end of the array like we were doing with the heaps, the problem you have is you have to shift things around or start marking things as deleted, which slows down our access time. You have to do a lot of patching, right? Same with inserting. Like, there's no easy way to insert in an array. You have to like shift the entire array forward, which is an O of n operation potentially, right? If you're inserting at the beginning of the array. So the pro of the array is, of course, quick access time. And why? Because you can use pointer arithmetics and say, I want to get the 10th item in the array. You know, it says an array of integers. All it does, the computer says, okay, integer size of 4. You want to go to the 10th spot. So I'm going to multiply 4 times 10, 40. So just move 40 bytes down the RAM, get the piece of memory you want. Boom, done. One operation, constant time. Sweet. Constant time, right? That's super fast. Like super fast. Okay? But O of n time for delete/insert, which is super slow. And why is that super slow? Well, because we have something like a linked list, right? And the linked list solves this problem by using pointers, which are great, right? They solve the problem of being able to insert because all we do with the pointers is we play around with them. We just basically say, okay, we want to insert right here. Great, just make a brand new node, hook it up to there, and then hook this one there, and you're good to go. How long does that take? Well, it takes constant time as long as you're already there. But if you want to locate the spot where you got to insert, that does not take constant time. That can take O of n time. So that actually brings up another point. The disadvantages of linked list is in search time. So the time it takes for you to locate where you want to insert or you locate what you want to delete, because again, with linked list, you can delete it in constant time. Bam, done, deleted, right? All you got to find out is the location, and then you just got to basically, I mean, heck, if you don't want to, if you want to have memory leaks, all you got to do is just change a single pointer in a single linked list. Just update the pointer and bam, it's deleted. It's still a memory leak, but okay, if you want to have a memory leak, then call delete on that pointer. You know, make a temporary pointer, copy that address, change the new pointer, and then call delete on the old pointer. Bam, done. Still constant time. So linked list solve the issue with arrays of insert and delete, but the cost of that is in search time. So what did we do? We said, why don't we kind of morph them together into a monstrosity that we called the tree, and then we came up with binary search trees, right? Well, binary search trees, while great at the beginning, very quickly became degenerate trees, right? We got all these nasty trees that were like just basically a linked list. So what did we do? We applied ABLs. We said, okay, let's balance a tree, because the whole point of doing a tree is being able to have a log n height, which is faster than n. So now we have the same capabilities of a linked list that we can insert and delete very easily in constant time. We don't have to resize anything, but we have lowered the insertion or the search time from n to log n, right? That's the whole purpose of trees. The whole reason we did ABLs, to lower the search time from n to log n while still retaining the capability to insert and delete as needed without resizing. So keeping that insert and delete at O of 1. Now, technically speaking, The insertion and deletion is all of one, but you've got to locate where to insert log n. So everything is technically log n, but you get the idea. But the question is, can we do better? Can we still want to be able to achieve that access time that arrays have, that O of 1 time is our goal. That is the dream that we're trying to achieve, that O of 1 access time, but still be able to insert things in O of 1. So can we make everything constant? Can we make insert? Can we make delete? And can we make search? The three big important things. Can we make them O of 1? That's the big question, right? That's what we're trying to go after. And the answer is yes. The answer is yes, we can make it. And that answer is, of course, what we are talking about, which is hashing. So, how does one achieve this power? Well, let's talk about something called a direct access table. Turns out that a direct access table is the answer we're looking for, but not the one that we want, actually. Okay? So, let us come to the most overused example, but yet useful, so I'm going to do it for hashing. And that is a phone book. Okay? So, suppose that you have a phone, and you want to use your phone, so you get your friends' phone numbers, and you write them down. So, let's just come up with some fake numbers. So let's say we got 305 and then 999. So I guess you live in like Miami, because I think that was the area code back when I lived there. 1122 and then 305. 345 or 303? I don't remember now. That's sad. It might have been 303. And then 305 999. You know, you're all like got your phone number around the same time. Maybe some person got it at a different time. 185. And then you got your friend from like LA. You know, I'm bothered. Is 305? Is that? Hold on. 305 area code. Okay, that is Florida. Okay, but then where is 303 from? Ah, that's Denver. Okay, so this is why I'm confused. See, I lived in both Miami and Denver, and then in Miami it was 305, and then in Denver it was 303. So that was just like a brain thing, censored. Beep. So yes. That is why I'm confused. And I was confused also back then. That's like, why are the numbers so close even though we're like in a different part of the country? So, yes. Okay. Which was better? Well, they're completely different. I mean, one's like super hot and the other one's like cold. So, yeah. I mean, I like them both. So, yeah. I like them both better than Vegas, I'll tell you that much. At least weather-wise. But it kind of is nice to not have massive amounts of rain, though. Yeah. Okay, so all right, so we got a bunch of phone numbers here, and the question is, you know, each of these are related to a specific person. So let's say this is like Jane, John, Kevin, Nick, and then Rachel. Just names, okay? So you got a bunch of names and you got a bunch of phone numbers. And so if you store these in an array, then you have to sort them, first of all. And if you sort them, then you can use binary search and achieve that log n time, right? But again, if you insert a phone number, you're gonna have to resize, which is gonna take n time. Okay, you do it as a binary tree, or you do it as a linked list. Then same thing, you gotta sort them, and after you sort them, search time is gonna take n time, and it's gonna take n time. It actually doesn't matter if you sort them or not. With a linked list, it's still gonna take n time to search. You can insert easily and can delete easily in constant time, but searching will still be n whether or not it's sorted, so you might as well not sort them. Finally, we do an ABL tree. With an ABL tree, we can definitely we could definitely make it balanced and achieve log n time for searching and then constant time for insertion deletion. Now, you're using not the names, but the number to do this, whether you're sorting at the array or you're building the APL, right? Okay, I would like to suggest to you another idea, which is what I'll end the lecture with. Let's make a big array, like a big array. In fact, how big of an array do I want to make it? I'm going to make it... Okay, I screwed up the commas. Hold on. That number, 10 billion. Okay, and I can achieve that in the computer. Why not? I mean, I got like lots of RAM. I got 16 gigs of RAM, so I'm fine. Okay, this is only like, I mean, if this was bytes, this would be kilo, mega, giga. This is like 10 gigabytes. So I can fit this in memory. Well, yeah, it will be 40 because each one's 4, so not quite. Actually, I got 32 gigs of memory, not 16, but still not quite. But it's okay. How about this? I'll make it half. Okay? And here's the thing. If I make it half like that, that means that all of these numbers can be indices in the array. Like the exact full number as it is an exact match for an index, right? So that's literally like array index 305 999 1122 is literally an index in my array. It fits in there. If I do that, guess what? In that spot in the array, I can go ahead and store James's name. Or I can store a pointer, that way the array is small. And it's not, otherwise the array is like massive because of strings. So then it definitely doesn't fit in memory. So yeah, if I do that, I can store it. And guess what? Because I can store it in that index, it takes O of 1 time to access. And guess what? If I have a new friend and their phone number is like 111111111, I just store it in that spot in the array because I have a spot already for that allocated. The only problem right now is I only have for the numbers up to 5 and the first digit. But if I had a bigger computer that could fit the 10, then I could fit any possible digit number here. And guess what? That's O of 1 in insertion, deletion, and search. Bam, I have solved the problem. Why did I even take the time to teach you APLs and all this other stuff if I could just do this? Well, because look at the size of this. That's pretty big. That's 40 gigs of RAM at this point. That's a lot, right? But hey, I solved this problem and, I can just buy more RAM and fit it. And so it's this sort of temptation as to do this as to why hashing is so useful, because what I'm going to do with hashing next time is we're going to keep this sort of awesomeness, but not have to make a 40 gigabyte array. But at least this gives you a teaser as to what's to come. So we'll continue this example next time. But hopefully that sort of raises your interest as to why hashing can be so cool and useful. And hey, there's no pointers with hashing, at least most of the time, unless you go into a special thing, which I don't even want to mention, but yeah. Is it going to use my PC? No, I don't think so, because I haven't figured out what assignment it is. But if I try to make you a direct access table in your computer, then yes, that would definitely kind of nuke it, as you would put it. So, yeah. But, all right. That was a fun lecture. So, hashing next week, hashing next Wednesday, hashing next Monday. No class the Wednesday after that because that's Veterans Day on Wednesday. And then the Monday after that will be the exam. So the exam will cover up to the hashing that we hopefully finish on Monday. And if we don't, then it'll cover what we covered on hashing. So, all right then. Good luck in your assignments. Let me know how that goes. And then if you redeem the extra credit, make sure you send me a message with your real name so that I can give you the points on Canvas to the right person. Especially for people who have similar names. So yes, on the 16th. So 2 weeks from today. So gives you some time to finish hashing. So yes. All right then. I'll see you guys on Wednesday. Stay safe out there. Especially tomorrow. Be safe.